introduce you.
Okay. You see is this?
Yeah, we can see it. And lots of green too. That's great. Well, happy St. Patrick's Day, everybody. I'm pleased to introduce Tian as one of our candidates for our research associate position. Tian actually got a Bachelor of Science here at the University of Texas in 2013. Then he went on to do a master's in 2015 and then a PhD in 2020 at Rice University with Jeff Nitrower. He returned to his beloved university and is now a postdoc working with Tim Gouge. Yeah, and Tian is a geomorphologist working on sediment transport and fluid flow, and he does both field and he has both field and theoretical expertise. His thesis work focused on applications to the Selenga Delta and Lake Baikal, and that's what he's going to be talking about today. But right now, he is working with Tim Gouge on applying his expertise to channel networks on Mars, and I'll look forward in the future to seeing what comes of that. So, Tian, take it away.
Okay, you hear me okay? Yeah. Okay, thank you, John, for the introduction, and thank you for everyone to come joining this talk during spring break. And in this background image is showing the Selenga River Delta that forms at the margin of the active Baikal Rift Zone. Hopefully in this talk, I want to show some of the work I've done here over the past few years to explore the sediment transport dynamics at this tectonically active river deltas. And why am I so interested in river deltas? This is because river deltas are an important component of the overall coastal systems. And it can act as a sediment filter at the coastline, so a gateway at the coastline. So over short timescales, hydrodynamics in the delta can drive sand deposition. And that actually dictates the size of supply sediment that feed other downstream coastal systems, such as barrier islands and the shelf. Here I'm showing an image of the Mississippi Delta during a spring flood in 2001. And as you can see, the brown sediment-laden river plume is covering most of this coastline. And the sediment-rich water is nourishing, the downstream barrier islands, beach, as well as the continental shelf. And today, delta systems are actually under a lot of stress. And for example, here I'm showing land loss map of the Mississippi Delta, both historical and projected land loss from 1930 to 2050. And these red areas are land that already been lost or projected to lose in the next 20, 30 years. And this is all due to human and climate impact. And so land loss in deltas, it is a coastal hazard. This land loss reduces sediment supply to other coastal systems. It reduces the ability of deltas to buffer against storm surge and future sea level rise. And we have learned over the past several seminars that Category 5 or intense severe storms, their frequency are increasing in the upcoming decades. So that makes the coastal community even more vulnerable against these natural disasters. And as a long-term resident in Texas, I have experienced several major hurricanes. Just as example, this is the Bolivar Peninsula, the aftermath of Hurricane Ike in 2008. And this is right around the time I just moved to Houston. And the more recent one is flooding caused by Hurricane Harvey in 2017. And this is Buffalo Bayou. And we're looking at downtown in Houston here. And for those of you who are familiar with Houston, this is at the cross section between Montrose and Memorial Drive, very close to where I used to live. So it's very important to understand delta land building processes, which is one broad theme of my overall research, is to understand land building processes in delta to combat coastal land loss. And one of the primary ways that delta actually build subaerial land around the coastal regions is through this process of delta lobe avulsions. Here I'm showing an animation of delta lobe avulsion of the Mississippi River Delta during the Holocene. As you can see through several avulsions, the Mississippi Delta is able to build subaerial land around the Louisiana coastline. And these different colors represent different age. And these avulsions can be driven solely by the internal process from sediment and water transport in rivers. Just to explain this very quickly, if I draw a cross section here at the main stem of the Mississippi River, we can see a schematic of the channel cross section. The gray area are the floodplain, and the blue is the water flow in the channel. And this channel have a bank flow depth of HBF, and then the yellow are mobile substrate of alluvium that's moving downstream. And over time, through transport water sediment, this substrate alluvium can kind of grade over time. And over time, this aggradation actually gets very close to the bank. So it's almost fill up the channel. And then a subsequent flood event can trigger overbank flow that eventually leads to a new flow path selection that the river connect to a new flow pathway for the river to connect to the coastline, shown in the schematics in this animation here. And we can quantify the time scale of this process. We can approximate it using this relationship here, which is the delta lobe avulsion time scale, TA, can be approximated using the bank of flow depth divided by the vertical aggradation rate of the substrate. And this is a function of sediment transport, sediment discharge rate in the channel. And this process can just arrive internally from the river, so we call this the autogenic lobe avulsion dynamics timescale. And deltas also experience external impacts coming from the downstream. For example, subsidence can occur from both compaction and tectonics, as well as sea level change. And this we term it as the autogenic impact, the external impacts. And this impact can also come from the upstream, such as varying water and sediment supply that's driven by climate or tectonic change in the source area. And these allogenic impacts can also modify the delta lobe avulsion timescale. Through multiple avulsion cycles over time, and then given the ideal basin configuration, delta actually are not sediment filters. In particular, through these multiple avulsion cycles, delta can prograde close to the continental shelf and actually connect to the submarine channels. And in this case, given the right conditions, delta actually became a bypass system where everything supplied to the delta actually, bypass the subaerial portion and is directly transported into the deep basin. And in this case, we have limited amount of sediment that is actually moving around the coastline during short time scales. And because delta system actually experience boundary impacts from the downstream and the upstream over geological time, delta stratigraphy actually is a very informative record of past climate and tectonic conditions from upstream and downstream boundaries. And one of the very pristine sediment sinks for delta stratigraphy is rift basins. Here I'm showing an example of a rift basin from Ireland. This is the Western Irish Mineral Basin. About 300 million years ago, these stacked stratas are the two lake cyclone. They're delta deposits that lasted around 10 to 100,000 years cycles. And it has been documented that these earthquakes, these rift basins experience discrete subsidence events driven by earthquakes, in addition to the conventional time continuous subsidence. However, how earthquakes and these discrete subsidence events impact delta morphology and stratigraphy and coastal hazard has been under study. So another broad theme of my research is to understand the impacts of these earthquake events on delta land building and develop of stratigraphy. So to attack these two themes, I've been working at a tectonically active region, the Baikal Rift Zone. So here I'm showing a map of Eastern Asia, and the Baikal Rift Zone forms in this black box region. And it is a rifting event between the Eurasia plate and specifically the Siberian craton in this region and the Amerindian microplate. And this rifting event started about 35 million years ago and is still ongoing today. If we look closely into this region, here I'm showing a bathymetry map of Lake Baikal and the Selenga Delta. Lake Baikal is the deepest and the oldest freshwater lake in the world. In the central basin, maximum water depths exceed 1,600 meters. And this lake extends about 700 kilometers in the long axis, and the width is about 80 to 90 kilometers. It holds almost 25% of liquid fresh water in the world. And the Selenga Delta forms at the southern shore, is arguably the largest lacustrine delta in the world. Covers about 600 kilometers square subaerial land. And because this delta forms near this active rift system, it actually experiences earthquake quite frequently. So here I'm showing a map of the delta and the lake again, and these circles are, the size of the circles here are earthquake locations and magnitude, ranges from magnitude 3 to magnitude 8. And these are some of the focal mechanism of the earthquake, of the fault slips. And this data is covering about the latter part of the 20th century. And some of these earthquakes are quite impactful to the delta. Here's another map of the delta system and the lake. And these embayments, this open water area close to the lake, are actually formed by the earthquakes. So these earthquakes actually can downdrop a significant part of the subaerial delta, below the lake level. And they occur, on average about every 1,500 years. And the most recent one occurred in 1862, forming the Provo Bay. If we look into this red circle, here I'm showing a geographic survey map made by the Russian Geography Society immediately after that 1862 event. So here on the left are the old distributary channels, and here are the open embayments. Just to help you better understand this map, here in this red line, I highlighted the post-earthquake shoreline. And this dashed line here is the pre-earthquake shoreline. So everything in between these two shorelines, the blue polygon actually are subsided below water instantaneously overnight. And you can see these labels here. I think there are actually fishing villages, that's on the delta. They just disappear overnight. And the maximum subsidence has been documented to be up to 7 meters. And because of the subsidence, reduce the delta area, it actually increase the gradient to this coastline by increase the regional slope. And it also creates this new accommodation. So it actually triggered a delta lobe avulsion, which attracted many distributary channels to flow into this area. And over the last 150 years, the shoreline has prograded to roughly about this spot, this dotted line. So it has infilled this area indicated by green. So given this quite active system, I aim to answer some of these following questions here. So for the Selenga Delta specifically, I want to understand how hydrodynamics in the channel network impact sediment grain size variability, and how does these subsidence events driven by earthquake impact delta lobe avulsions. These are the color scheme denote to the time scale of the process. And then from what I learned here, I want to say something general about deltas at active margins. So first is, by answering two questions, what can we say about the development of stratigraphy in the basin? And can we develop a practical model to predict flow partitioning in the distributary channel? So to address these questions, I have conducted field work in the Selenga Delta in the past few years. And here I'm showing a map of the Delta again, and with the white lines highlighting the 7 main distributor channels. And these different symbols are our survey transects from 4 different field surveys starting in 2013. And at each of the locations, I have measured channel cross-section profiles, flow velocity, water sediment discharge, and river bottom sediment samples. And here just a photo, just some example of the field work. I have photos showing the field work. We stay in very nice hotels in the Delta, in the presidential suite, and because we have very big showers. And here are just some photos of me collecting velocity data, sediment samples, and measuring channel geometry. And after data collection, we bring some of the sediment back to the States to measure their grain size using this particle size analyzer. And here just some example of the sediment grain size in the channel bottom. And as you can already see, there's a very big difference in grain size. These 4 samples are quite coarse. And here we have a very sandy. So it's already very interesting. And we can look at how this grain size changes throughout the Delta. Here I'm showing a plot of bed material size in millimeters as a function of distance downstream of camp. So this camp area is near the Delta apex, so the main river part. So 40 is the lake and 0 is the upstreammost part. And this grain size is in log scale here. So the observation here is that grain size finds downstream from gravel to sand. And gravel actually disappears somewhere downstream on the Delta. And we can look at this in plan format as well. Here I'm showing a map of the Delta with the 7 distributor channels highlighted. And the white lines here indicate mixed sand and gravel channels. And then the black lines indicate sand bed channels. So the observation here is that for these different channels, gravel terminates downstream at some point, and they terminate at different locations. So I want to investigate what is driving this gravel deposition. First, we want to characterize the distributary channel network. To do this, we borrow a concept from the tributary system, channel orders, and this is a relatively easy to use concept. Basically, the main river is an order 1 channel and bifurcates into order 2 channels, then to order 3 channels, and so on. And we identified about 8 channel orders, and we can plot channel order as a function of distance downstream of camp. Again, camp is this white star here near the apex. What we observe is that as we move downstream, channel order increases. This just implies that as the channel moves downstream, it creates more and more bifurcation. Next step is to quantify how flow changes as the river bifurcates. And we have measured water discharge and velocity in the channel network. And here these 2 plots are showing bankful water discharge as a function of channel order, as well as flow velocity as a function of channel order. The observation here is that both these flow parameters decreases downstream as the river bifurcates. And we can translate this into shear stress, which is a proxy for sediment transport capacity shown in this plot. So here is shear stress in Pascal as a function of channel order. So as a result of flow reduction, shear stress, the sediment transport capacity also decreases downstream, which is caused by flow partitioning. And now we can compare how this actually impacts transport of gravel. To do this, we use a simple metrics, the gravel transport stage, T. And this is just a ratio between force of the river flow to shear stress to the force needed to initiate gravel transport. So if this parameter is greater than 1 or equal to 1, we have gravel mobility or gravel transport. If this is less than 1, we don't have gravel transport. And here are some the more explicit equations that calculate this transport stage. Now let's look at our prediction. So here I'm showing another map of the delta. The circles are our transects, and the color of the circles indicate that transport stage parameter. So the white circles indicate the river has some capacity to transport gravel, and the black circles are where we don't have, the river doesn't have the capacity to transport gravel. After we make this prediction, we can check our field measurements, which is shown in this map. So here the circles are our transects, survey transects, and then the color scheme is the same from last slide. And then the lines are observed river bottom composition, which the white is mixed gravel and sand, and the black lines are sand channels. So we have agreement between measured and predicted gravel transport. So it confirmed our finding that gravel deposition is actually driven by this reduction in shear stress due to the flow division in this highly bifurcating channel network. So this answers our first question, which is how do hydrodynamics in the distributed channel network impact grain size variability? The answer is that the grain size finds downstream from gravel to sand near the coast. This is driven by a reduction in sediment transport capacity in the distributed channel network. And broadly, this finding to the broader coastal community is that the broader implication is that distributed channel network actually could, over short time scale, reduce the supply sediment science to other coastal systems. And one of the advantage of doing international work is to enjoy nature and culture at Baikal. So here I'm showing some photos from the field, and the Lake Baikal is a very beautiful place, and there's some local people live here for many centuries. The Brayats, they're part of the Mongolian group, and the lake also have its own seal, and this is independent from any ocean or coastal seal. Has very independent evolutionary track, which is very cool. And then just to remind everyone that we know that these discrete subsidence events triggers delta lobe avulsions on the Selenga Delta. Here I'm showing a map of the delta again. In particular, I'm showing the elevation map as well as the bathymetry map of the lake. And this black line here is the 1862 shoreline, and the green is more recent, around 2002 or so. As you can see, this eastern part of the delta has prograded significantly over the last 150 years or so due to this lobe avulsion. And as I showed in the background, we know this autogenically, this external delta lobe avulsion, the real occurrence timescale is about 1500 years. And we want to understand how this compared to the internal dynamic, which I also explained earlier, that driven by this in-channel aggregation, the internal autogenic avulsion timescale. And for the delta system, we can approximate this using the slope of the fan, the radius of this delta, as well as the basin water depths. To do this, I conducted a remote sensing survey on the delta. In particular, I set it up a semicircular survey grade with 25 kilometer transects. I survey around this semicircle, so at a space of 1 degree. So I have 180 transects where I survey these 3 different parameters. I also compiled shorelines using both historical maps and Landsat images. So that covers the last 152 years, so from 1962 to 2019. So I can measure shoreline dynamics since the lobe avulsion driven by this tectonic subsidence event. Here I'm showing shoreline progression since that earthquake, and this graph here on the y-axis I have radius of the delta, and on the x-axis I'm plotting year, and this eastern lobe is the region of delta that experienced that subsidence. So this part of the delta has been prograding, at a long-term average rate of 26 meters per year over the last 150 years. In contrast, the central lobe, which is the delta area that's adjacent to where the earthquake occurred, actually, because of the avulsion, it lost all the water and sediment supply, so it experienced coastal erosion. So the shoreline actually retreated about at a rate about 13 meters per year over the last century and a half or so. So this just further confirm of finding of how tectonics subsidence can trigger delta lobe avulsion. Let's continue to try to constrain this internal autogenic avulsion timescale. First, I have measured delta slope, and this plot is showing elevation above sea level of the subaerial delta as a function of distance downstream of delta apex. And these gray lines are all 180 transects. And then I took an average showing in this dash line. And then I can, from this average profile of the delta surface, I can calculate a mean slope of the delta, as well as the radius of the delta. Next, I can constrain water depth in this embayments. Here is a plot I've shown earlier of the delta, where I highlighted the distributor channels with their channel bottom composition, and these are the two embayments that form around the delta. And our Russian colleagues have conducted bathymetry surveys here over the years, and we can constrain their water depth in this area. So on average, the water depth is about 2.5 meters, and this is just a histogram showing the depth distribution in these two embayments. So now we have all the parameters we need to constrain this internal lobe avulsion timescale. And after considering uncertainties on all these parameters, as well as calculation errors, I'm plotting a probability distribution of the internal lobe avulsion, the autogenic lobe avulsion timescale here. And here I'm reporting the median and plus minus the 25 and 75th percentile. So the median is about 9,200 years. But the range is quite large. And we can compare this back to our autogenic avulsion timescale. Again, this is the map I have shown earlier, the elevation map of the delta, as well as the bathymetry. We know that earthquake occurs roughly about every 1,500 years, which triggers avulsion on the delta. But the internal dynamic from rivers, water and sediment transport driven avulsion occurs 9,200 years. And this autogenic avulsion time scale is much, much longer than the tectonic time scale. And we can conclude that, at the active margin, subsidence events actually could predominantly trigger delta lobe avulsion, in contrast to at passive margins where, avulsion are predominantly driven by autogenic effects. So that answers our second question. At active margins, delta lobe avulsion could be predominantly triggered by tectonically induced subsidence events. And from a coastal hazard standpoint, coastal delta systems near tectonic active regions are actually at risk of earthquake-triggered flooding, which I don't think haven't been considered before. And from understanding of this tectonic subsidence impact on delta lobe avulsions and the grain size variability, we can make some implications. It has implications on the development of stratigraphy. One of the effects is that it actually changes the preservation style of delta stratigraphy. Here is the image of the delta again. I'm showing a seismic line collected in the 90s by USGS and Russian Academy of Science collaboration. And this is very old seismic data, which is shown here. So on top is an old seismic 2D seismic line. And here on the bottom is the interpretation by Scholz and Coleman et al. In the late 90s. And in the paper, they documented these shallow water delta deposits. That's supposed to be at water depths of 10 to 20 meters, actually appears in really deep water, in 400 to 600 meters. And if we observe this more closely, we see, it seems like there's blocks of these delta strata that internally they have very complete cladoform structures. I can highlight them using these polygons. Here, I can observe about 5 of these. I will argue, these are actually downdropped blocks, created by these discrete subsidence events. So the surfaces that are actually bounding them are not time continuous. So that's one of the implications from these subsidence events. Another one is the arrested gravel front. So here I'm showing a schematic of the Selenga Delta, and from my earlier part of the talk, I show that gravel terminates some point downstream, shown by this gray area. However, the gravel inflow is time continuous. So this gravel front must prograde downstream over time. And then if we draw a transect here, look at this in the dip section, which is shown in this schematic here. In order for the gravel to move downstream, you must to grade the channel bed enough to create a steeper slope to overcome this, this reduction in shear stress to move downstream. And we can constrain how fast this occurs by calculating this gravel timescale. Right? So we can calculate this volume that required to grade to this new slope divided by the gravel inflow. That's roughly about 1,700 years. And this is calculated using a transport equation developed by Wilcox and Crow. And we can compare, and then we know that earthquake actually generates more space around the delta. And that's about 1,500 years. And this two time scale are very similar. So the implication is that the delta actually creates accommodation at a faster pace than the infilling of gravel. So essentially gravel is trapped on the subaerial delta and only mud is transported to the basin. And to test this, we come back to the data from the USGS and Russian Academy of Science collaboration in the 90s, where they had several cores in the delta front. If we look at their core data, which is shown here, and most of the cores consist of mud with very little sand, and they're very fine-grained sand and in the cores. And some of the longest cores about 5 meters. Given the low sedimentation rate around the delta front, that this represents about around on average about 35,000 years in time. So over that time span, at least there's no gravel transfer into the lake. So just to summarize, the earlier findings have strong implications on the development of stratigraphy in the lake. In particular, gravel over relatively short time scale, multiple millennia, gravel is actually trapped on the subaerial delta, and only mud is transported to the basin. And from coastal system standpoint, this actually implies that coastal distributor networks over long time scale could reduce the supply sediment size to the basin. And we also found that subsidence events could be preserved as discrete blocks of stratus. And this implies that interpretation of coastal stratigraphy at active margins should be aware of this abundant discontinuous surfaces, because we have these discrete blocks. Their contacts are not time synchronous. And a lot of this work a lot of this research are conducted with a lot of help in the field. So I actually had a lot of assistance in the field from locals as well as some animal friends. This is our dog. This one of the dog at the camp. She was guarding our sediment samples. And this local fisherman, he really loves my Jackson School hat, so I had to give it to him. And then eventually, leveraging all this data and finding from the Selenga Delta, it prompted the need to develop a practical method to predict flow partitioning in a delta network. So here I'm showing a schematic of a distributed delta system again. And the need to do so have several reasons. First, today, most of the gauging stations, so field data that constrains discharge going into the delta are actually several tens of kilometers or hundreds of kilometers upstream of the delta. The circle indicates a schematic gauging station. So we really don't have any idea what's going on in the network itself. And current modeling method have some limitations. So they either really focused on local scale, so looking at division of flow at a single bifurcation, or it requires detailed bed bathymetry of the entire network. That could be very costly in time and instrumentation. So this prompted me to hopefully develop a practical method. And to do so, I rely on this new method to model flow partitioning using a directed acyclic graph. To explain this very quickly, I'm showing a very simple graph here with 4 nodes, 1, 2, 3, 4, and they're connected by 4 edges, showing here. And directed, meaning that there's direction of information flowing. So we know information is flowing from 1 to 2, indicated by the arrow here. And acyclic indicate that there's no recycling of information. So whatever goes to node 2 doesn't come back to node 1. And we can use this concept to approximate flow in river deltas. Here is an example of a very simple schematic river delta. And we have a simple graph, the exact same graph here. And then we can represent the flow in this delta, in this graph, mathematically using the adjacency matrix. For example, here, we know the flow is going from node 1 to 2. And to show this in the adjacency matrix, we have a non-zero entry in row 2, column 1. So the non-zero entry represent a connection between bifurcations. And then the row and column indices actually represent the flow direction. And just as another example, we know 1 and 3 is connected. There's a non-zero entry in row 3, column 1. And we can also look at how strong the connections are using the weighted adjacency matrix. Here, just the same example, in row 2, column 1, we have a number of 0.2 that just indicate 20% of the flow is flowing to this node 2 from 1. And here, row 3, column 1 have 0.8 that indicate 80% of the flow is from 1 to 3. So essentially, this weighted adjacency matrix actually just contain information about how flow divide at a bifurcation. And traditionally, how flow divide by at a bifurcation is approximated using channel width ratio between the downstream channels. So B here is channel width. So discharge in the downstream branch can be approximated using a nodal relation like this. So discharge in this branch 2 equal to the width ratio of the downstream channel times the input discharge. So I have tested a range of remote sensing variables to determine what's the best nodal relation, to use in this overall graph framework. And after some investigation, what I find is that the combination of channel width and sinuosity actually give the best predictions. And just show this quickly. Here's the sinuosity, just the actual length of the river in L divided by the straight length of a river bed. And just to look at how good this parameter is, here I'm showing a graph of predicted water discharge using this nodal relation of this is discharge in the downstream branches against our measured water discharge. And these two parameters actually give really good prediction in the downstream branches. for water discharge. We can also look at this, how good the prediction is for total sediment discharge, which is shown here. And these data indicate that our model is actually give pretty good predictions, so we can move forward to further develop our graph. Here I have mapped the graph of the Selenga distributor network. This gray area, gray circles are different vertices, so different bifurcation and confluences in the delta. And just to remind everyone, the eventual goal is to construct this adjacency matrix, and then combine this with our splitting flow division rules at each bifurcation to predict flow everywhere in the delta. And now I'm showing the prediction of the graph model. So here I'm showing the network of the Selenga Delta, and these circles are survey locations, and different color lines represent this parameter F. So this is the discharge in that particular branch normalized by the main input. So the maximum number would be 1 or 100% at the main stem, and then it can go as low as 0. So for example, these gray lines around the fringes indicate these branches only partition about 5% of the total inflow. And the purple line here is between 20 to 50%. And since we have these field surveys, we can test how good our predictions are. And here I'm showing a plot of our predicted water discharge using the graph model against measured discharge at those survey locations. Overall, the model does a pretty good job. We can also do this for total sediment discharge. It's not as good, but the R square is only about 0.45. Yeah. Overall, the model does a decent job to predict both water discharge and total sediment discharge. In addition, I also tested how good this model is to predict time series data. So just an example, I will show predicted hydrograph at this particular location here in this red circle. So here I'm showing hydrograph at this location over 2.5 month period. So we'll have water discharge at the y-axis and time on the x-axis. And this solid line here is showing measured hydrograph that we measure in the field. And this dashed line here is the graph model predicting the hydrograph. And we can also look at how the model did for total sediment discharge. And the color and line scheme is the same. Overall, the model does a pretty good job predicting time series data. So it has the capability to predict, given the ongoing climate change, how climate-induced variability in water sediment discharge actually impacts flow partitioning in the delta network. To further test our method, I applied it to several other delta systems around the world. One of them is the Selenga River Delta in Russia. And this delta system drains into the Russian Arctics. And here I'm showing the model prediction, which have the similar color scheme. And our prediction actually agrees really well with field measured data at these gauging stations. I applied it to another place in the States. The Wax Lake Delta is part of the overall Mississippi River system. And again, the model prediction actually agreed pretty well with our field measurements. Just to summarize, can we develop a practical model to predict flow partitioning? Yes. And more importantly, this model actually uses remotely sensed variables. So it has very broad modeling application for understanding changing flow partitioning in large-scale delta systems worldwide, where field data are often limited or very hard to collect. So just to summarize from all this work and how some of the finding here, what are their implications for coastal processes? Finding in the Selenga Delta indicates that distributor networks could reduce supply sediment size to other coastal systems over a short time scale. And for tectonically active basins, distributor network could also reduce the sediment size supply to the basin. and delta system at tectonically active basins are at risk of earthquake-triggered flooding. And interpretation of coastal stratigraphy at active margins should be aware of these abundant discontinuous surfaces, as these subsidence events actually sequesters a chunk of the subaerial delta. And we also develop a method to model flow partitioning in large delta systems, and that can be applied quite easily. And given my interest in fluvial coastal processes and stratigraphy, as a postdoc currently at the Jackson School, I have been working on a project to use property of channel belt to hopefully identify river types, so single thread braided river types in the rock record. And the reason why I'm using channel belts is that it is a quite common sedimentary deposits, both for the modern and the ancient settings and across planetary surface. Here I'm showing maps of several different channel belts. In A is the modern Brazil River channel belts, and in B is the channel complexes on Mars. This is the Aeolus dorsa. And in C, this is the ancient channel systems showing seismic data in northern Gulf of Mexico. And in D is outcrop data from the Green River Formation in Utah. So they're quite common everywhere. And the goal is again to hopefully identify what kind of river formed this. So currently I have just 3 categories, and I'm hoping to expand to expand river types more quantitatively. So currently I just have meandering river and branching and braided. My current finding is that the sinuosity of the river branch actually changes, have very distinct distribution. So in this plot, I'm showing cumulative distribution functions of sinuosity of these 3 different river types channel belts. The finding is that as the branch number actually decreases, the CDF, the tail of the CDF actually become heavier. Currently, I'm working on theories and more statistic methods to quantify the heavy tails. And given my interest in fluvial and coastal systems at UTIG, I'm interested to develop more projects to looking at coastal hazards. One of the projects I'm interested in is looking at flow partitioning between engineered structures at the Gulf Coast and the natural systems. Here I'm showing a map of the Freeport, Texas. And this area is a mixture of large cities and natural areas. And if we look at this more closely, this landscape are actually filled with channels. So we have the cyan green is showing artificial canals and engineered channels, and the red lines actually indicate somewhat natural channels. And just to name them, we have the Brazos River going here, we have the intracoastal waterway, as well as the old Brazos River. And this project, I aim to use the graph model to understand how water and sediment partition between these different channel systems and what is actually making into the Gulf to understand sediment supply to other coastal systems. And this is great interest to the climate and polar research groups work on sea level rise at the institute. And potential funding agencies include the Sea Grant of Texas, the General Land Use Office, which is very close to campus. And this area actually is high value of national security, given the intracoastal seaway, and the large refinery and liquid natural gas terminals in Freeport, and the strategic oil reserve buried along the coastline. So Department of Defense and Bureau of Ocean Energy Management are actually good funding agencies as well. The broad goal of this project, to find a balanced solution to optimize structural function of engineered products and sustainability of the coastline. Another project I'm interested in looking at is to develop a project to look at sediment dispersal dynamics at both active and passive margins. So here I'm showing a bathymetry map of the Selenga Delta, where large submarine canes actually connects to the delta, subaerial delta, where sediment gravity flows can travel down these canyon and to deposit sediments in the basin. And a direct analog in the passive margin is the Mississippi Delta, the modern Mississippi Delta, showing this NOAA bathymetry data, where we have the Mississippi Canyon leading very close, building very close to the modern birdfoot, the subaerial delta lobe. And this kind of delta and canyon configuration occurred in Texas as well through geological history. Here I'm showing a map of the Texas coastline here, and this colored scheme are actually ancient incised valleys that formed on the Texas shelf during the last glacial maximum. And these channels are filled with sediment, particular sand. And I'm interested to look at how the filling of these valleys differ similar between active and passive margins. And this actually complements the sand-seeking project at the Trinity Valley, led by John Goff and Sean Goic and Chris Lowry, and that interests many funding agencies. And the overall goal of this project can help constrain sand resources in the Gulf or worldwide. And then the final project I'm interested in is looking at how storm hazard varies spatially along the Gulf Coast. And this is because the Gulf Coast actually have very spatially variable sea level rise rate and morphology. In this NOAA bathymetry map of the Gulf, in the northern Gulf is quite shallow. The shelf have quite shallow gradient, and in the northern Gulf have very shallow gradient. On the southern Gulf actually have very steep gradient. And another map of the Gulf actually shows very spatially varying sea level rise rate, shown by tidal gauge data, as well as changing erosion and accretion dynamics. So these different colors actually shows movement of the shoreline. So given these heterogeneities, I want to build models to make localized prediction of storm hazard, giving the increased frequency and magnitude of future storms. So with that, I will conclude my talk. And I just want to thank my collaborators over the years, as well as support from my family and my wife. Thank you.
All right, thanks, Tian. We're open for questions now. If you have a question, please raise your hand and I'll take you in order. So Duncan, you're up.
Hi, yeah, nice talk. I guess maybe just expressing my naivete on the subject, but does the density of the medium that you're going into matter, i.e. the fresh versus salt water for the deltas?
Yeah, yes, that's a very good question. Yes, that actually was the original. That was the original hypothesis that actually led us to investigate this delta, because the idea is that lake water is always have lower density than the sediment-laden water coming from the river. So the idea is that the sediment-laden water always plunge into the lake bottom. You know, they move as a gravity, like a hyperpycnal flow, versus ocean-going systems where the salt water is actually, you know, have very similar density to the sediment-laden water going into the ocean. So in this case, you form a much larger hyperpycnal, a river plume that actually can disperse sediment in a further spatial extent. So for my system in the Selenga, we do see this effect. The sediment plume are actually smaller. You know, they don't extend as far. And the idea is that they might just plunge at a shorter distance moving downstream. And this is one of my interests to kind of explore, you know, how is this impacts the sediment gravity flow in the delta front. Yeah.
Thank you.
Yeah, hope that answers your question.
Okay. More questions? Now I got a question. So I'm really interested in that strain of the let's say strain partitioning, flow partitioning. What is it? If you can predict flow partitioning, what does that really gain you in terms of practical applications?
Yeah. So one thing it can tell us is that given a change in the hydrograph coming from the upstream, we can evaluate how different areas, which area of the delta are more prone to flooding, overbank flooding. And another way is that there's because we know flow partitioning now, we can kind of using some existing method, we can actually predict the risk or the likelihood of how bifurcation will, whether they will close or they will remain open. That actually kind of changes the routing of material in the delta as well, and changes the flood risk. So, but yeah.
More questions? Charles, go for it.
Let's see. So I guess what I want to know is whether your observations that are made when it's not raining, or let's say there's not a big event, apply where I guess a lot of the sediment might be transported during large rain events.
So you wonder whether
your observations are applicable, because you're not necessarily, I think you're viewing it like a steady state system, right? With, steady input and, and everything's kind of like kind of an equilibrium kind of push of sediment out. But I guess an alternate picture would have it that most of the sediment transport occurs during discrete events, let's say through a large precipitation event or something.
Yeah, that's a good question.
Or let's say, why does your model work so well when I'm assuming that a lot of things happen during big events?
Oh, okay, yeah, that's a good point. So the model works really well for, it is a steady state model, you're correct, and it works really well at least for water and total sediment discharge, because they actually equilibrate fairly quickly on a fairly quickly timescale. And what doesn't really work well for our model is actually predicting bed load flux, because that kind of transport is more sensitive to extreme events. And that's part of the future work that I'm interested to work out. And then currently, just given the current state of the model, because bed load of transport amount is a small fraction of the overall sediment load, is about like 5%, is not as critical at this point. It's not as critical for like a rough estimate of the flow partitioning, but for more precise estimate, we want a better prediction of the bed load partitioning.
Okay, I think I'm going to have to talk to you more during my half-hour session.
To
understand how much big events shape the delta. Anyway, we could talk more later.
Okay.
Thank you.
Thank you.
All right, time for one last question. And if there are none, well, thank you, Tian, again for a very interesting talk, and we'll see you later. Oh.
Thank you.
All right, take care, everybody.